In this video, we're going to determine how many of these molecules are polar. Polarity shows us that the atoms in a chemical bond are pulling on each other, creating partial charges on the atoms. So in order to find the polarity, we're going to draw the Lewis structure for each molecule, and then we're going to identify the bond dipoles using the differences in electronegativity. And from there, we're going to identify the net molecular dipoles based on molecular geometries. So we're going to start with SO3, and since S is less electronegative than O, we're going to put it in the center, and we're going to bond the 3 oxygen atoms to the S. To draw the Lewis structure, we're going to find the valence electrons for this molecule from the periodic table. So we know that S has 6 valence electrons, and each O atom has 6, and there are 3 of them, which is going to give us a total of 24 valence electrons. We already know that we have 3 bonds, which is 6 electrons, so we can subtract the 6 from the original 24 to give us 18 electrons that are going to go around the O atoms to make octets. So we can start 2, 4, 6, 8, 10, 12, 14, 16, and we notice that S will not have an octet if we put the 2 non-bonding electrons right here. So rather than putting them here, we're going to make a double bond here, so that way S can have an octet and fulfill the octet rule. So we know that sulfur is more less electronegative than oxygen, so we're going to give it a slightly positive charge, and each oxygen atom is slightly negative. This is going to help us create our bond dipoles. We can determine the domain geometry and molecular geometry to determine whether or not the molecule is polar. Since SO3 has 3 domains and they are all non-bonding, this is a trigonal planar domain geometry. And because there are no, these are all bonding. Because there are no non-bonding electrons, the molecule is also trigonal planar. So to draw the bond dipoles, we're going to start at the more, from the less electronegative atom and go outwards towards the electronegative atom. So each one of these is going to be equal, and it's going to start at the sulfur and extend out to the oxygen. So we know that each of these bond dipoles are equal, and because the molecule is trigonal planar, all the domains are equal, which means that all 3 of these bond dipoles are going to cancel out, which is going to give us a non-polar molecule. Moving on to OF2, we know we're going to have O as the center atom because it is less electronegative than fluorine, and the valence electrons are going to be 6 for the O atom plus 7 for each fluorine atom times 2 fluorine atoms, which is going to give us a total of 20 valence electrons. We already have 2 4 electrons that are being bonded, so we can subtract 4 for a total of 16 electrons that are going to help make octets. So we start on the outer atoms. We have 2, 4, 6, 8, 10, 12, and we haven't reached 16 yet, so we're going to put the rest on the center atom, 14, 16. This domain geometry, although the Lewis structure looks linear, actually is tetrahedral because we have 1, 2, 3, 4 domains. The non-bonding electrons count as domains. So this is a tetrahedral domain geometry. But the molecular geometry is bent because there are two non-bonding pairs. So the atom is in fact going to look like this. With these non-bonding pairs bending the pulling the fluorines together. So because of this molecule, our dipoles are going to extend. We know that oxygen is slightly positive and the fluorines are slightly negative because of the electronegativities given to us from the periodic table. So when we draw our bond dipoles, they're going to extend from oxygen to fluorine. These bond dipoles are not going to cancel out. They're going to create a net dipole on the molecule that is going to be downward from the less electronegative O atom to the more electronegative fluorines. So since the net dipole is moving downward, that means we have a polar atom, a polar molecule. So next we're going to do BeCl2. Beryllium is going to go in the center and it's going to bond to the two Cl's. We know that beryllium has 2 valence electrons and each chlorine has 7, which is going to give us a total of 16 valence electrons. We can subtract 2, 4 from the bonding pairs to give us 12 electrons that are going to go on the outside of the chlorine atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you notice, the beryllium does not fulfill the octet rule. It is an octet violator because it only has 2 valence electrons. Therefore, in the Lewis structure, it will not have any double bonds or non-bonding electrons on it. This is a correct Lewis structure. So since this only has 2 domains, 1, 2, this is going to be a linear domain geometry. Therefore, the molecule is also linear. This means that the bond dipoles are going to extend from the more slightly positive beryllium to the slightly negative chlorines. So the plus is going to extend. The plus goes on the positive side, and the dipoles extend towards the more slightly negative atom. Because this molecule is linear, these dipoles are going to cancel out, which means that there is going to be a net dipole of 0. So this molecule is nonpolar. Next, we're going to do CCl4. So C is going to be in the middle with 4 Cl's bonded to it. For these valence electrons, we know that C has 4 and each Cl has 7 for a total of 32 valence electrons. We have 2, 4, 6, 8 already used, which is going to give us 24 electrons to put non-bonding pairs on this Lewis structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. This Lewis structure has 4 domains, 1, 2, 3, 4. Therefore, it's a tetrahedral domain geometry. And because all 4 of these domains are bonding, the molecular geometry is also tetrahedral. When you draw the bond dipoles, you know that carbon is going to be less electronegative, and the chlorines are going to be have a slightly negative charge because they're more electronegative. So the bond dipoles are going to extend from the carbon out to each Cl atom, and they're all going to be equal. This molecule is not going to look like this. It actually looks somewhat like this. So the dipoles will look like this. Because all of the domains are equal, all of these bonds are going to cancel out and there will be a net dipole of 0, which means that this molecule is nonpolar. And last we have ozone, O3. And we know that each O atom has 6 valence electrons, which gives us a total of 18. And we have 2, 4 from the bonding, from the bonds. So this gives us 14 electrons that we are going to use to create the Lewis structure. 2, 4, 6, 8, 10, 12, 14. So we notice that oxygen only has 3 domains. It does not have a complete octet. So this means we're going to want to take one non-bonding pair from either one of these outside O's, oxygens, and create a bonding pair with the oxygen in the middle, so that way there can be an octet on the central O atom. So it doesn't matter which one you take, but I'm going to take